Hey, thanks everyone for attending. Right, so welcome to the one-on-one on CAT content compression. So Steve already mentioned I'm Tobias. If there's any questions later when you can't catch me today, there's my Twitter handle, just hit me up. I also welcome lots of feedback, especially critical questions about the tools I'm going to present on. So feel free to contact me. First of all, to make sure that you're in the right room, here's what you will learn today. So we'll talk about the quality metric in JPEGs. We talk about how it might not be the ideal place to compress JPEGs with. We'll look at the dissimilarity index as a valuable alternative for this. We'll talk about different JPEG encoders and compare them. And we will have a look into quantifiable data sets to see how well they're doing in terms of compression, how much you can gain when you deploy one of them. We will have a deep dive into the image saliency mapping and how saliency maps can actually help JPEG encoders do their work better. And last but not least, we will talk about how you can automatically arrive at a very sane quality setting for JPEG compression instead of compressing all your images with a standardized setting, which will improve visual quality of images and reduce file size. So this is what's happening today. If you don't feel comfortable with that, if you are very happy with that, yay, excellent, you're in the right room. Right, so our story begins. In Soviet Russia, data roams you. So here's the little story. When you're with Deutsche Telekom as a mobile provider and you roam, what happens is in certain countries you have limits on your data caps on your data for roaming. So you can't browse the web as long as you want. Telecom classifies countries into how much data cap they put on, and in Russia, it's 50 megs. So after 50 megs, your data connection just gets capped. That's what happens. So let's say you wanted to have an extra tool on your hands, say the LG Watch, to help to tell you that you always have new mail, because this is what smartwatches are for, right? You always have new mail. So you want to open the LG Watch website while you're in Russia, while you're roaming. Here's the bad news. The LG website for the smartwatch is 54 megabytes of data, and most of that is images. The reason is they are shipping all resolution images to all users instead of targeting them. They want to make sure that when you switch viewports, you have all the right sizes available all the time. So they give you 54 megabytes of image data, which is a terrible thing to do, right? So what you end up doing is this. Because after the 50 megabyte cap, you still don't have that website. Your data plan just expired. You have no information to go on, so you might just as well throw your phone away. So to avoid scenarios like this, and if you're working on products and you want people to open this website wherever they are, of course you can implement workarounds, right? You can use async for image loading. Async all the things, excellent. Which is a good approach. Or you might just as well thank this guy. Sitting right here, Joaf, who basically fixed responsive images for us. With his help, now we can load images in different sizes for different devices, and we don't need to ship high DPI images across the board. That's really great, and Joaf fixed that for us. That's excellent. At the end of the day, however, we do need images, no matter what size, because we need to convey emotions on our websites, right? We want people to take an action, and for people to take an action, we need to convey some sort of emotional trigger. That's where we need images. My emotions, my emotions. And there's also data on that. So with the help of Steve's HTTP archive, we can clearly show that image byte size has a huge impact on page load time, both on desktop and on mobile. So this is why lots and lots of talks this time at Velocity are actually focusing on images, because images are the new frontier. I mean, we've gzipped, we've subfleet, we've done everything to text-based things that is possibly imaginable, but these binary blobs of images are still a huge problem, and lots of people are not dealing with them. That's why there's no real way around the heavy lifting. We need to learn the tools to deal with these binary blobs, these images, and make sure that we compress them as strongly as we compress other resources. To do that, we need to understand the tools available to us, right? Okay, so the first tool I'd like you to introduce you to, because that's really important across the entire talk, is the dissimilarity index. Okay, who hasn't heard of the JPEG quality setting? Please raise your hand. Okay, everybody, excellent, that's good. So the JPEG quality setting is a nice thing to make sure that you compress your images weakly or strongly, right? But with the dissimilarity index, we can actually detect how much difference there is in an image after it has been compressed, instead of relying on this JPEG quality setting. So you get a number back, which is between 0 and 1, and has 6 digits after the comma. And with that, you can judge how much the image has changed when running it through a certain encoder. And this index is really helpful because with SIM, with DSIM is the dissimilarity, SIM is the similarity index. With the DSIM, we have a very good guideline of how much the human eye will actually be able to see differences after encoding. That's a really helpful index, and I'll run every encoder we're going to encounter now through the dissimilarity index and show you how good it does. Right? Okay. How DSIM works is it compares PNG versions of images against each other in order not to be confused by what JPEG compressors do to the images. So you first have to convert a JPEG losslessly to PNG, which basically results in a very huge PNG. And then you compare an input PNG to an output PNG, and you get that number back. So that's what you see here. I'm just using image magic, converting the input image, converting the output image that resulted from the encoding, and then comparing them. So, like I said, I'm bothering with this because the JPEG quality setting might not be ideal. When I say might not be ideal, I'm actually not telling you the entire truth. It's actually less than ideal. And the reason is it's not standardized at all. Giraffe actually dropped me a message a couple of weeks ago and asked if the quality metric was standardized, and I didn't know, truth be told. So I dug into the standard, read the RFC, and it's not. So there's no mentioning of standardizing that quality metric whatsoever. So when you take the quality metric of, let's say, 75 right now, because that's a very common number in JPEG compression, and you put a quality of 75 to one encoder then to another encoder, that's not, you can't expect the same result. These numbers are not transportable from encoder to encoder. The reason is because under the hood, all these encoders do very different things. So they optimize the tables differently that they encounter for JPEG compression. They do very, very different things. So you're basically comparing apples to oranges. And this is why we need a reliable metric to compare the encoders by, and this is why I bothered with the dissimilarity. Okay, let me introduce you to the picture you'll be seeing plenty today. Weird guy eating flowers on an island, right? So when I'm compressing that image, what happens is I get a different output image. And with the dissimilarity index, I can actually detect these differences. Differences are here colored in red. And the number of pixels that are changed or blocks that are changed can be counted and expressed in a number. Okay? Any questions through dissimilarity so far?
How are you calculating differences? RGB,
That's Lumina and Chromina tables, so different channels. Okay, so let me introduce you to the first encoder. Now that we've encountered the dissimilarity, you know what the number is I'm going to show you. So let's talk about the first encoder. Who hasn't heard of JPEG Optim? Oh, wow, okay, nice. JPEG Optim is a command line tool available in all major Unix distros. It builds upon libjpeg, which is also available in all major Unix distros. And what it does, it just feeds smarter information to libjpeg and makes sure that that the output is acceptable. So it's basically an optimization layer around libjpeg compression. It's very old. The earliest version of JPEG Optim is 14 years old, I think. But it's well maintained. There's a GitHub repo. I linked it, yay. And development is still up to date, so that's pretty nice. And JPEG Optim is doing a good job. So if you are running a Unix-based server and you're thinking about doing JPEG compression, getting JPEG Optim is really easy because it's really available in every major distro. You can just install it with any package manager. You don't even have to bother with Homebrew or anything or compile from source. It's just available in all packages. So getting that is really easy. Here's how JPEG Optim works if you run it from the command line. So I'm stripping all EXIF data. Who of you knows what EXIF data is? Excellent. Okay. So EXIF data means that there's additional information stored in the image, which describes, for example, the camera model taking the image, time and place, geolocation, and all that kind of stuff. It's mostly text-based information. You can also store other stuff in EXIF data, but that's more hacky. Plainly told, EXIF data contains text information around the image. When you ship this, you have to ship the text data too, which of course makes the image bigger. And there are edge cases showing that sometimes the EXIF data is much bigger than the image itself, especially when encountering small images. So you have actually a lot of more information text-based than the image data itself. That's where we need to drop EXIF data if we want to ship the image to the end user. Drop.
Are there any tools out there that can selectively keep some field in the EXIF data, like copyright, etc.?
Yeah, there is. There are specific EXIF data removers, and you can blacklist and whitelist in the command line. So when you want to build a photo database, of course, you might want to keep EXIF data. So a good practice might actually be to keep EXIF data for a master image, but when delivering the image to the end users over the wire, they're dropping all EXIF data because you don't want to ship this to end users. It's just extra padding that nobody needs who's just using a web browser. Then there's a thing called all progressive. That means it encodes the image progressively. Of course, Tammy and Kent have already given their talk about how progressive might not be the best idea. Until I've seen a second study that proves that, the study that Neurostrata did with Redware, I'm still on the track of suggesting that progressive JPEG is a better idea than baseline JPEG. Who can tell me what a baseline JPEG is? Oh, cool. Okay. So, okay, yeah, Joel. A baseline JPEG means that the image is downloaded in one go, and you basically have this rolling window effect. So you can see the image coming in if you have very low bandwidth from top to bottom. We know that when you're on a slow mobile, or if you have a few semesters on you, you also know that from modems back in the days. So you know these images coming in very slowly. That's a baseline JPEG. To get around that, there's this progressive encoder. And what that does is it ships the JPEG in different layers. The first layer is very tiny and doesn't really resemble the image at all. Most of the time, it depends on what's the content of the image. But it enables the browser to already identify width and height of the image if you didn't set this. By the way, you should always set image width and height in your HTML to make sure that the browser has an easier time finding the correct size. And it gives the user the perception that something is already happening. And then layer upon layer, like a cake, the image is built up until the final image has been retrieved. It causes the image to be slightly larger than baseline, but the considered best practice, at least until the Neurostrata research, was that progressive JPEG gives you a better user experience because you already see that something is coming up and you already know the final dimensions. You don't have that rolling window effect. That's why progressive was considered the best practice. Okay, so the last thing I'm just doing is piping the output into an output file, right? That's how I run JPEG Optim. Okay, the input image you've seen, the island holiday photo, is 5.7 megs. Of course, that doesn't resemble most of the images on the web. Don't worry, we'll go into a quantifiable data set later on. So I'm running this through JPEG Optim in the command you've just seen. Is anybody, by the way, doing this with me right now? Is anybody demoing this live while we're talking here? All right. Okay. So I'm running this. I'm running the command you've seen here with this image, 5.7 megs, and I'm getting this down already with that simple optimization to 5.3, which is not a huge gain, right? But I've gained this by dropping the EXIF data, and this is a lossless encoding because I've not dropped any quality. And that's why I also get a dissimilarity index of 0, because I've actually not dropped any visual impact on the image. So there's nothing that the dissimilarity index can detect as a difference between the input image and the output image. That's basically what lossless compression is all about, right? So 5.7 to 5.3 is not a lot given. So there must be a way to go faster. We must get that image smaller if we want to ship this. Okay, let me introduce you to lossy compression. The image we've just seen, I took with my smartphone. That was a Nexus 5 and a quality setting of 92, and it was unoptimized at 5.7 megs, right? That was pulled directly from the camera. And now I am introducing the max parameter, same command, max parameter, which basically says there's a cap on the quality that the JPEG is supposed to have. And this is now dropping information, image information deliberately. And we're getting down to 0.79. That's much better. That's actually now shippable. And this is still 4,000 by 3,000 pixels, right? So this works. And this is why we now have a dissimilarity of 1.9%. Like I said, the dissimilarity index is actually between 0 and 1, and then 6 digits after the comma. But oh, by the way, the creator of the dissimilarity index is actually in the room, Cornell. Hi. But we can just, by shifting the comma, we can just create this as a percentage, which is readable much more easier on these slides. So don't be confused by that. So now that we've dropped some information, we actually have some artifacts here which are invisible at that resolution right now. But that's why the dissimilarity index is now able to detect some difference here. But at least we got the image down to a size where I would feel comfortable shipping that. But there must be a possibility to get even more out of that. I mean, with tools that are available to everyone, right? It must be possible. So let me introduce you to JPEG Rescan. Who of you knows JPEG Tran? Cool, okay. Excellent. JPEG Tran is a very old tool to optimize Huffman tables on JPEGs. And JPEG Rescan is nothing but a Perl script which wraps around JPEG Tran and brute forces that optimization. It's a nasty hack, but it works very well. Written by somebody involved in the creation of H.264. And you can just get that Perl script on GitHub, and you need JPEG Tran, which is available on all Linux distros. And it just runs JPEG Tran often, shifting the math behind it, just to make sure that you get the most optimized Huffman table for the input image. Because JPEG Tran basically runs once on an input image, and therefore it has a very high probability of not giving you the optimized Huffman table, while JPEG Rescan, like I said, tries to brute force that, runs it often, and tries to find an Huffman table that is more precise for the current input image. Okay, so I actually wrote an article about this and tested JPEG Tran versus JPEG Rescan on a quantifiable data set and proved that it's, I think, 1.2% more effective in image compression than JPEG Tran itself. Okay, so let's run JPEG Tran. I'm telling it to be quiet, JPEG Rescan, otherwise it's quite verbose. And I'm giving it an input image and piping it to another. I'm not even piping it, I'm just outputting. And this I flag is an optimization for JPEG Rescan that makes it a little smaller, so I'm getting the most file compression that I can possibly get. So after JPEG Rescan, I mean, we were at 0.79 and now we're at 0.78. We saved 10 kilobytes. And between the 0.79 and the 0.78, we still have a dissimilarity index of 0 because the Huffman table optimization is lossless again. So we're not dropping any optimization. This is just smarter math. This is just a compression table that enables JPEG Rescan, JPEG Tran, basically under the hood, to do a better job. And this is how we save another 10K. Okay, like I said, that holiday photo. Oh, no, before I get into that. Any questions on JPEG Tran or JPEG Rescan? Oh, okay. So, like I said, that holiday photo is not ideal, right? Because who ships 5.7 megs? Hopefully nobody, at least if you're not running a photographer's site. So let's do it for science. Once more for science. I wrote a script that randomly selects or pseudo-randomly selects JPEGs from the internet. I'm doing this by getting HTTP archive headers, looking for JPEGs, and downloading them, verifying that the JPEG is actually in JPEG, because as probably most of you know, You can also do hacky things, like say that a file is one type while actually sending another. So I'm also verifying that I'm getting a proper JPEG back by doing some header verifications. So I'm actually knowing, so when I run the study, I actually know that I'm running them on JPEGs and not exploits hidden as JPEGs. So this script has gathered almost 1 million JPEGs by now, but I've calculated that with 12,000 JPEGs, I have a data set that is statistically significant. So if I run the same study on larger image sets, I'll just get the same result. So this actually makes things faster for me to test. So I think I've got these 12,000 images, right? And this is how the pseudo-selected JPEG image set looks like. This is JPEG quality distribution, read with image magic. We have what I call the Google Images spike at 75. This is because Google encodes all JPEGs that they ship on Google Image Search at 75, and a couple of other sites have picked that up too. So when you randomly select JPEGs from the internet, you'll find always that there's a high spike at 75. This is because large companies have gone to encoding JPEGs at a quality setting of 75, no matter what encoder they're using. Why this might not be a smart idea, we'll get into that later. Then there's the 80, which is considered the last best practice before the 75 became popular. And it is also one of these settings for Safe for Web. At 85 and 86, we have the standard JPEG setting when you save with tools like the GIMP or any other Unix-based image optimization tool. Then we have a huge spike at 90. This is mostly unoptimized images from cameras, from smartphones, because they mostly encode at 90 or 92. And these 94, 95, as well as 99 and 100 are DSLRs. So this is JPEG quality high on a normal camera, and this is give me all the quality possible on a DSLR. So this is completely unoptimized image data. This is the quality distribution of the 12,000 JPEGs we're running the study on now. And this is the file size of the 12,000 JPEGs. So most of them, as you can see, more than 6,000, are actually smaller than 10K. I was really astounded by that. I hope you are too. So I dug into the data and actually had a look. By the way, don't open 12,000 JPEGs in Finder. That just doesn't work. So when I wanted a preview of the 12,000 JPEGs to find out why so many of them were so small, that was actually a hard thing to do. But after a while, I got around the whole issue of not being able to open such a large data set. And I found out that lots of people still use JPEG for the wrong things. So for example, buttons, which can be created with CSS nowadays, or small icons, which would be ideally served as SVG, or at least PNG8, right? But lots and lots of websites that have been scraped by HTTP Archive actually do that. They use JPEG for tiny, tiny images, which is not ideal. But they still do that. That's why there's this huge data set of small images. Then we have this nice slope towards images larger than 100K. So we've gotten to know our data set. And now I've run JPEG Optim and JPEG Rescan on that data set. And here's the quality distribution afterwards. The compression efficiency afterwards. So there's a small amount of images colored in slide red over here that are actually now, after the encoding, larger than they were before. This actually tends to happen depending on how weird the input image is. This is expected. So this is a completely natural thing. And then we see this nice curve, this nice bell curve over here. And we see that it peaks around 9 or 10. I'll get to the median number in the next couple of slides, and it slopes out. So and this is actually more than 100%. This is also a calculation edge case, because probably these images that you can see at the right end of the scale are probably these images that are really, really tiny. So there are a couple of hundred bytes, and running through an encoder gets them down to a couple of dozen bytes. This is how more than 100% of compression efficiency are possible. So the median of that, which is of course more important than the bell curve itself, is 12% for JPEG Optim and JPEG Rescan. That means, a takeaway for JPEG Optim and JPEG Rescan, you can right now deploy JPEG Optim and JPEG Rescan on any Unix-based server, run JPEGs through them once they're uploaded, and get a mean 12% out of them, no matter what marketing or any other department uploads to the CMS. That's a nice win, and it's really easy to deploy. Like I said, it's available at every major Linux distro. And with a dissimilarity of only 0.02%, that's excellent. That's really great. That means there are probably no visible artifacts. So when you use JPEG Optim and JPEG Rescan, there's a very, very low likelihood that somebody from another department will come by and bug the front-end team about, oh my God, the JPEGs have artifacts after I uploaded them. This is what happened in other companies. When you deploy image compression, sometimes somebody goes around with the iPad and goes like, the large hero header photo now has artifacts after I've uploaded it. So with JPEG Optim and JPEG Rescan, compressing images at 12% more efficient, you can be pretty sure that you won't have visual artifacts. That's a nice takeaway. However, there are alternatives. So the most modern alternative is WebP. Who has heard of WebP? Excellent. That's exactly the same result in every room I'm in. That's fascinating. Last time I actually joked that Google has a great marketing team because I'm always astounded that so few people have heard about JPEG Optim, but everybody has heard about WebP. That's amazing. Okay, so WebP is like the new kid around the block since the last couple of years, developed by Google and now open source. And what Google tried is basically solving the image compression problem on the web once and for all. So they made a format that can replace PNG8 by only shipping 256 colors if it wants to. It can do full alpha transparency, basically everything that PNG24 could. By the way, all in smaller file size than the original formats. It can do lossy compression like JPEG does. It can do animations like animated GIFs are famous for, right? I'm using animated GIFs on this slide deck all over the place. Terrible. And they all do that with a stronger compression. So WebP actually beats most of these file formats in file size while being able to ship all these formats. There has been some heat against WebP, mostly from high-def photography scenes and game engine developers. That is because WebP is not catering towards these needs, these use cases. So what WebP is actually trying to achieve is solve these image problems on the web and not solve game engine problems, right? So when you think about WebP, always think about all the binary encoders we have right now for images in one go. That's WebP. So let's see what WebP does for our holiday photo. I'm inputting the, bless you, I'm inputting the 0.78 compressed JPEG and giving that to WebP. Let's see what it does. So when you install WebP, that's available also with Homebrew, and I think they also have Debian packages pre-packed, so it's easy to install. You get CWebP and DWebP binaries, CWebP to compress WebP, and DWebP to decompress WebP. I also tell WebP to be quiet, because WebP otherwise is also very chatty on the command line. Oh, by the way, all the people taking photos, the slide deck is already up on Speaker Deck. So if you want to see those commands, just head to tobias.is. That's my website. You found the Speaker Deck link in the footer. You can see the slides right now if you want to. If you want to see, check the commands some more. So I'm telling CWebP to be quiet and giving it an input image and defining an output WebP image. And after that, I'm down to 0.46 megabytes. That is an amazing compression, truth be told. That's really nice. The dissimilarity, however, is higher than with what we've seen with JPEG Optim and JPEG Rescan so far. WebP is really, really good. As you can see, the compression level is amazing, but of course that comes at a price, right? So when I'm calculating the dissimilarity, we have a higher impact on that. How to do that? You have to use the decompress WebP tool again, because WebP is that format that is not supported anywhere else. So you need to use the pre-packaged DWebP binary to actually deal with WebP images. And I'm creating a PNG from it so I can calculate the dissimilarity. And like I said, we have this support problem with WebP. WebP actually only works in everything that's Google-based. So it works on Blink and Android, and that's about it. So when you want to ship WebP, you have to target the devices you want WebP to have, because most of the browsers out there don't support WebP right now. So you have to dive into client hints headers or anything that could give you an idea if that browser your server is currently talking to will actually support WebP or not. Okay, to make sure that I'm not just having an odd moment with the holiday photograph. Oh, hey, Joaf.
Just one point regarding WebP. All the browsers that support WebP advertise that in the accept headers that they send out for images. So you can use that on the server side.
Excellent, thanks. Did everybody get that? Okay, all the browsers that support WebP advertise this in the accept header, so you can read that and ship WebP to them. Thanks. Okay, to make sure that we also can prove that WebP actually does a good job across the board and not just on that one photograph, let's run the 12,000 image data set through WebP and let's see how well it does. Here's the compression efficiency curve for WebP on the 12,000 data set. So you can see we have some images that are larger after the compression. But like I said, this is just natural in a data set of this size. This just proves that this whole thing is actually working. And we have a very, very nice bell curve here without any large outliers. And this is actually, the beauty of that bell curve actually shows how much engineering time has probably gone into WebP, because getting that nice of a bell curve in image compression is really hard. So I'm pretty sure that the Google engineers have spent a lot of time shaping WebP to be the way it is right now. So this is a really good result if you see that nice bell curve here. As a median, WebP is able to compress images about a third stronger. This is a really great takeaway. I mean, that's 1/3 down of the block right now when you use WebP. That's really efficient. However, like I said, this comes at a little cost. If you remember, JPEG rescan, JPEG optim was 0.02 in a dissimilarity, while we have a mean dissimilarity index for the 12,000 image data set of 0.3%. So we do have some more lossiness when we ship WebP. Okay. Any more questions to WebP so far? No? Okay, thanks. So the newest kit on the block that is really kicking it up, and I really love that, is mods.jpg. The reason being, there have been contenders for new image formats. WebP, of course, and there's JPEG XR by Microsoft, which was locked up in open source license struggles for a while, and then I think it kind of slowed down in development, while WebP actually was, I think, LGPL2 from the get-go, so that was picked up a little quicker. However, the whole problem with developing a new image format is that you need support across the board, right? So Mozilla and lots of others actually thought, why not fix the problem at the source? We have JPEG already. JPEG is supported everywhere. Why develop a new format and have all the browsers needing to implement this? Why not fix JPEG compression? Because JPEG is there. So they went ahead and created a new tool, a new encoder to fix JPEG compression. This is a graph from their first study in November 2013, in which they proved that WebP and other formats are actually not doing that much better than expected. You know, like Google, of course, had studies showing how well WebP is doing, and everybody who was developing new image formats showed how well their image format is doing. And then Mozilla launched that study and showed, well, actually, they're very close together. Everything is very close together. So if we just invested in optimized JPEG compression, we can actually get JPEG to this kind of compression level without losing visual quality. So why not invest in this? So they did this. Mods.jpg is very, very smart when it comes to nerdy math. So all the table optimizations that are needed when you do JPEG compression, like Lumina tables, Chromina tables, all that, this is what Mods.jpg focuses on right now to get better compression. What's the bleeding edge about Mods.jpg I'll get into later. So let's see how well Mods.jpg is doing on the holiday photograph. I'm giving it the 0.78 input image with no EXIF data. And here's how I'm using it. Mozilla chose to go with CJPEG for compressed JPEG. I'm using the 75 quality. And this is actually not necessary. I'm just doing this for the slides. This is on by default. So I'm progressive encoding, etc. So you don't even need to have these two flags. And then I'm giving it an out file. And what I'm arriving at is 0.76. Not as strong as WebP at the first go, but hold your horses. Look at the dissimilarity. You can see that it's, again, very, very neat. It's very close to what we've seen with JPEG Optim and JPEG Rescan, and actually got the image smaller. And this is, like I said, because it's very smart about what it does under the hood. To show you that, let's run that also through the 12,000 image data set. Here's the compression efficiency distribution after running the data set through mods.jpg. Again, you can see there are these small outliers to the back, which are now larger after compression. Like I said, this is completely natural. And you have that bell curve again, which is a little steeper here, but it's also very, very nicely engineered. You see no major outliers. So also a very, very good encoder. And as a median, that gives us 12.1% compression efficiency across the board. So again, you can say if you deployed mods.jpg right now on your servers to compress JPEGs, you would get about this gain in every JPEG you upload, median, of course, while not creating lots of artifacts in the JPEGs you're compressing lossy. So 0.09%, that's very, very decent. Any questions to mods.jpg so far? Everybody good? Cool, right. There are also proprietary attempts to solve the whole JPEG encoding problem. The most noisy one was in 2011 and 2012, a company called JPEG Mini. They got funding from Google and claimed they solved JPEG compression while still adhering to the JPEG standard. They vanished for a while after they got the funding. So there was actually the joke of, haha, somebody's now having a nice life on an island somewhere. But they actually resurfaced, and they're shipping the JPEG Mini tool for Mac for, I think, $20 for desktop, and you can get a enterprise server version of the whole thing for a couple of $1,000. And what it does is it smoothes a couple of colors. It tries to use a saliency mapper, which I'm getting into in a couple of minutes, and then compress the JPEGs. And this is the 12,000 image JPEG study compressed with JPEG Mini. Here's the problem. JPEG Mini, like I said, is closed source, so I couldn't really dive into what they do under the hood. I had to reverse engineer from the output images I got. I could only detect that some images were now smaller than the rest, but I couldn't detect how small. So these are images that failed to compress, but like I said, JPEG Mini does not give me any insight into how badly they failed. So I can only tell you that this is the number of images that were now bigger after JPEG Mini compression than before. And as you can see, we actually have more of a slopey distribution across the JPEG compression efficiency for the large data set. And well, from what I'd say, this means that the JPEG Mini compressor is not doing that well. It's not that nice Gaussian curve, the bell curve that we're looking for. Across the board, however, JPEG Mini hits in at 17.2% mean compression efficiency. And at a cost, of course. The dissimilarity index is 0.4%. So we're actually having more artifacts in the images now after that compression. So the reduced file size comes at a cost. It always does at some point. So all of these tools we've encountered so far have something in common, and that's they're trying to be smart about what's inside the image, what's inside the box. So this whole thing with let's just compress everything equally, every image is equal, that doesn't really work. So modern tools are actually trying to be smart about what they do with in terms of image compression. Before I get into the details of what that is, what they're doing under the hood, is there any more question about the tools, the encoders we've encountered so far? So there's mods.jpg and JPEG Mini right now. Any questions about that? comments? No? Okay. So in this whole effort of understanding how to be smart about what's inside an image, I created Adapt. Right now, I'd say over-engineered bash script that does nothing but slice JPEGs into tiles and tries to compress adaptively. So the whole thing started when I was working for a client, and I realized when I encountered my JPEGs that there were artifacts, and I thought, damn, there must be a way to get away with better JPEG compression without causing all these artifacts. Then I looked at where the artifacts were occurring. Can you make a quick guess where artifacts would occur if I was to compress this holiday photo strongly? Any guesses? Colin?
The white space. Right.
Why is that?
Isn't there an issue with the XOR deltas on the?
Oh, that's a very nerdy answer. Excellent. Could you go a little bit high level?
I'll leave it for you.
Okay. Any other place in the image where you would expect artifacts to happen if I ran this through a JPEG encoder? Pardon? Around the flowers? Okay. Ah, okay. Why is that? Excellent, thanks. So yeah, to generalize these two answers, so everywhere where we encounter these high contrast areas in between two colors, like the red roof and the grayish blue sea in the background, or the banana plantation leaves against the sky, these are high contrast areas where one color drastically switches towards another color with a distinct line. And this is where the JPEG compression always messes up a bit, and you can start to see compression artifacts occurring at these sharp lines. So when I thought about this whole thing, I thought, why not detect these lines? Why not find out where my high contrast areas actually are, and I can then tell the JPEG encoder to treat them differently than the rest. So I looked up how I would detect lines in an image. And the way I first went with is Sobel edge detection. That's available in ImageMagick and GraphicsMagick from the get-go. So it's an easy way to get this. And what I did is I ran an all-directional Sobel. So for edge detection, you have to tell the edge detection algorithm from which angle it's heading into the image to find edges. So I'm saying to Sobel, let's give me all the edges, so all around. So it runs around the entire image, fires its edge detection algorithm, and highlights these corners. And as you can see, we have high contrast areas here at the leaves, back there where the cars and the roof are, the mountain line, and my glasses. Oh no, somebody's glasses. That's not me. Somebody's glasses and hair. So this is where I expect artifacts to occur. Because, like I said, it might be that these high contrast areas are the places where the JPEG encoder might have problems. So that worked reasonably well. However, after a couple of months, I figured out that actually does not suffice for me. I want a proper highlighting of entire areas, because maybe I want to make sure that not only the corner itself does not get strongly compressed, but actually my face or the flower, because this is the part of a photo that's important, right? Nobody cares about the blurry background. I mean, the photo is shot with a little bit of depth of field effect, so the rest of the background is actually a bit blurry. That's not really important to the viewer. The viewer wants to see, oh, that's that guy, and he's doing this, while the whole background information is just like, it's a nice biowork. You wouldn't want a black background, but it's not as important, right? So I was looking into saliency detection. I read a couple of white papers and decided to go with a certain algorithm. I contacted the guy creating that at university and asked for his source code, and got one of my colleagues, Jed, who sadly cannot be here right now, to port that into C++. And then we open sourced it with the permission of the creator. And the algorithm is called the maximum symmetric surround saliency algorithm. And what it does is it highlights entire areas of an image for importance. It does that by analyzing chromina and lumina and a couple of other smart things, and then finding these areas and highlighting them in gray shades, right? So this is the output of the holiday photo run through the saliency detector. And as you can see, the leaves of the plants are highlighted, the roof, and my hair, my forehead, and the flower, of course. So they're highlighted. This is, however, not processable in an easy manner. So what I did is I dropped all the gray information and only to retrieve a black and white image, because with black and white, I can actually process that image bit by bit. So this is what the saliency mapper looks like in a programmatically computable way. So now I can run through the image and calculate black and white pixels. Any questions about saliency mapping? No? OK, great, thanks. So let's do that whole thing again. I have 0.78 megabytes and no EXIF data. I ran it through Adapt, got that saliency map, and compressed adaptively this time. And I'm down to 0.59 megabytes. That's very, very decent. I mean, look at where WebP was. That's a very, very good compression. However, I pay a price, high dissimilarity. 2.9%. That means I have visible artifacts in here right now. That's bad, but that's something that can be fixed. So to iterate again how that works, how I get to that kind of compression result, I do this by, I don't know, do you know that JPEG compresses in blocks? Does anybody know that JPEG compresses in blocks? Yeah? Okay, can anybody tell me how large these blocks are? Oh, Giraffe, you're always spoiling everything. Yeah, 8 by 8, of course. So JPEG walks along the image and compresses in 8 by 8 blocks. So what I'm doing is I'm hooking into that. And I'm saying this 8 by 8 block, this 8 by 8 block, this 8 by 8 block, and I'm treating them differently. If I ran this through a normal encoder like JPEG Opt-in, which we've seen at the beginning, the entire image would be encoded with one quality setting. While with my saliency mapper, I am able to see, hey, there's a lot of white in here. If there's a lot of white in here, maybe that area is important. Maybe I should compress that more weakly. Then I'm hitting a completely black spot, the monotonous sky we've seen in the original, right? Let's go back a few. See, completely monotonous. Also completely monotonous, the sea. Everything is just milky gray because it's in the background. There's depth of field. It doesn't really matter. So we can see that the entire area has been blacked because the saliency mapper decided this is not important. So if once my script hits a completely black area of 8 by 8 blocks, it just goes, that must not be important. Let's encode this strongly, because it's very likely that I will get away with high compression without causing artifacts. So I'm encoding all of that very strongly, again, again, again. Then I'm hitting the next row, and I'm starting all over again. Leaves, leaves, leaves. Very weak compression, not to cause artifacts. Sky, sky, sky. Strong compression, because I can get away with it. So when my script is done, it ends up with a couple of thousand tiles, 8 by 8, which are weakly and strongly compressed. Then I reassemble the whole thing and compress it as a single file and get a JPEG out that now has been forcefully, adaptively compressed, which was not possible with JPEG before. And that's how I arrive at this kind of result. But like I said, this comes on the price of high lossiness. So when I run this whole thing through the dissimilarity again, as you can see, it detects that there are these areas which have been modified strongly. And if you remember the saliency map, it had this slope towards the road and the mountains, while the sky and the sea were not important. You can see that the most dissimilarity is actually occurring in these blocks. So this is basically proof that the script works. To make sure that this encoder actually does its job properly, I also ran this, of course, through a quantifiable data set. So let's look at it again. This is adapt, and this is the compression efficiency of adapt. As you can see, again, there are outliers which are now bigger after encoding than smaller. And then we have this slopey thing again, and this is because adapt is just a bash script. It's not very well engineered like the nice bell curves we've been seeing in the past. but it does a good job at certain points, right? As a mean, a good job is defined by 29.9% mean efficiency. That is pretty good. That is almost as close as WebP. So there is a way to get JPEG to be just as small as WebP without breaking the standard. That's basically what ADAPT has proven. However, we do this, of course, at the price of high dissimilarity, which is tough, right? So when we want to encode JPEGs even more efficiently, we have to get that number down, because at this number, what happens is that people start complaining. They will be able to see artifacts in certain places inside the image, and they will go, this is not acceptable. Especially on modern screens, which are really good, you will be able to see the compression artifacts. So this is something we want to avoid. Okay, any questions about this whole approach? Yeah.
You said you went back to a black and white image.
Mm-hmm.
So the high compression, low compression is just a binary.
Correct.
You didn't think about trying a grayscale?
I did. That is on the roadmap. However, we're currently basically on a lockdown. We're not developing this as of right now, but our roadmap shows this, yes. What we're currently planning is 4 colors of gray, and thereby getting 4 different quality settings for the compression blocks.
And second question, what kind of how expensive is this stuff?
Really expensive. That's really bad. Processing time is terrible. Thank you for asking this. So no, it's totally fine. I mean, this thing is written in Bash, and I'm actually using stuff like a Bash calculator, which is probably one of the worst performing things there is. So adapt probably takes a couple of seconds per image, depending on image size. Sometimes even up to 20 seconds, which is awful. I mean, considering if you were running a large site with user uploads who constantly generate new images, if your server was blocked for 20 seconds with each image processing, that doesn't scale, right? But like I said, this is just a Bash script to basically prove that this is possible. JPEG will move into the direction of being able to do this in the near future and not in Bash. And this is, again, thanks to Cornell. We talked about this yesterday, I think, yeah. So Cornell actually sat down a couple of weeks ago and started implementing adaptive compression in mods JPEG. And that's plain C, and that's plain fast. So that's really nice. So ideally, at some point, mods JPEG will support adaptive compression properly, and I'll be able to completely abandon adapt. And at this point, we can, oh yeah, sorry, I had a thank you slide for this. So Cornell is actually implementing this right now. And at this point, if we get this, we actually have superhero compression, because we have mods JPEG very well maintained, very smart about what it does under the hood. We have adaptive quality compression. And if we solve this adaptive quality compression with a saliency mapper, which is also being discussed, that means we can finally have JPEGs which can compress very, very quickly and can compress as strongly as WebP does without incurring large artifacts, and while not breaking the JPEG standard, which means we will be able to ship this to every browser that's out there right now except from Lynx. So that's pretty awesome. So that's why I call it superhero compression. So if we arrive at this point, I think by this point, JPEG compression will be solved. So the main takeaway of this chapter is we need to be smarter as JPEG encoders. We need to be smarter about what's inside the image. This whole thing about encoding with one quality setting just is not right, because it causes quality issues all over the board. And as this quality standard is not standardized, the quality metric is not standardized, you cannot really use it and deploy a new encoder with it. So that's really not a smart idea. So we need to think about ways of being better about detecting what's inside images. So saliency mapping is the way to go, and adapting compression levels depending on saliency maps. That's probably where we need to head, and that's where we're heading right now. So let's talk some more about adaptive quality. Unless there are any more questions to this. Shoot.
Pretty large sample image for the adaptive compression, right? The 8x8 blocks
the question is, how bad does it compress? Adapt itself? Actually, Adapt is better in smaller images. So runtime performance for Adapt on large images is terrible, and it does a bad job at large images because it slices the image into these blocks, and every block that I am currently creating creates extra byte padding, which I need to get rid of after I reassemble the image. And the tool I'm using to do this is JPEG rescan, like again, based on JPEG Tran. And this can only do so much. So if I've sliced, say, 16,000 tiles into cache and compressed them and reassembled them, I have incurred so much padding that I might actually end up with an image that's larger than the input image. So Adapt is actually pretty bad at this right now. So the smaller the image, the better Adapt. Thanks for asking. So even more adaptive quality. So like we discussed plenty of times right now, the JPEG quality is actually bad. It sucks. It's not standardized. We can't rely on it, right? And depending on what the content of an image is, that doesn't really give us a nice output. So there was a tool a couple of years back called ImageMin. Correct me if I'm wrong. People who know more about image compression than I do, ImageMin, which tried to solve this issue. However, it's not very well maintained right now, doesn't work very well, so I just figured I'm going to create, yes, another bash script, because that's how I roll. But it just basically does the same thing that ImageMin did. And what it does is it tries to automatically identify a decent quality setting. And I'm going to try and demo this right now. Let's see if I can get this going, because that's actually pretty neat. So, where am I? Okay. No. Yeah, that's it. Right. Okay, so I've prepped this folder. And we've got an input JPEG that is the 0.78 input JPEG. And yes, you can see it already ran, but I'm going to rerun it right now. If I can get my cursor back, that is CJPEG. Right. So I've created this script, and it basically takes two input parameters, and that is the encoder to be used and the file to process. Right now, it only supports JPEG Optim and mods JPEG, but new encoders can be hooked in with one line of code, so it's really easy. And I'm basically creating a tool belt of different encoders I can run tests against. So let's run this with mods JPEG. It's going to take only a couple of seconds to identify, oh no, that's the large one, huh? That's going to take a little longer. So what it does now, under the hood, I'm going to show you the code in a couple of seconds, is it runs the compression of with mods JPEG once, finds out the dissimilarity index, and finds out if that dissimilarity index is acceptable within a certain range. If it is not acceptable by being too low, which means we could compress the image more strongly, it drops the JPEG quality and runs again. If it detects that the dissimilarity is already too high, that means that we already have compressed too much. So I'm raising the JPEG quality and re-encode again. Then I measure again, get the result again for dissimilarity, and find out if I'm now in the sweet spot that I want. Let me open the code. I think I should have kept that up somewhere. Hello. Ah, here we go. Click, maybe. Thank you. So, that's all boring sanity stuff. Here we go. So this is the configurations variables for this. So I'm basically saying that the first run with a quality of 80. And then make sure that we don't hit anything more than 100. by only being able to add or subtract nothing more or less than 20 in terms of quality. And then here's the important part, the dissimilarity index, lower bound and upper bound. The Neurostrata Radware research has indicated that a dissimilarity of 0.015 was actually acceptable by their tests with real humans, so real user studies. So I came up with, oopsie daisy. I came up with these numbers because when you drop JPEG quality only by 1 point, depending on what is inside the image, you might already be hitting outside of the sweet spots. You can't actually land on point at 0.015, but you have to be somewhere around this, somewhere close to this. So this is basically the realm in which I accept an image as being visually acceptable and not caring about the quality that it got. Here's the main function that just calls everything, and here's the tool belt that we're currently running. Mods JPEG and JPEG Optim. And like I said, this is basically the magic bit. All it does is it finds out if we should add or subtract to the current JPEG quality while running again, and waiting until we have hit that sweet spot. So basically, this is just as nice or just as bad as JPEG rescan because it brute forces the JPEG quality. So it finally happened, and I now have a output JPEG. And if I got the color, if I identify the quality setting, that is from that the resulting JPEG has, it's 59, which is really bad, right? I mean, people expect an image with a JPEG quality of 59 to have large amounts of artifacts, but actually it doesn't. Because that image, like I said, has this whole depth of field thing, lots of blurriness, so JPEG can actually compress quite well. So we can lower the quality very much without actually causing lots of artifacts, because that image I've been showing you has only very few distinct high contrast areas, while lots of blurriness is in the background. So if I was to use JPEG Optim or any other normal JPEG encoder, I would have to hard code my JPEG quality. So if I implemented JPEG compression in a CMS, I would have to set a setting, right? I would have to go like, when an image is uploaded, it is supposed to be at a quality of 80, 75, something, for all the images coming in. But as we have discovered, JPEG quality setting is not standardized. So who says that 75 is an ideal setting, or 80, or 82, right? And lots of people just crank up the quality because they don't want to be the ones responsible for when one image that marketing or anybody uploaded finally has artifacts. So they all crank it up to 90, which gives you huge images, bad web performance, and just to get around this whole artifact issue. But if we honed in with a basic binary search approach on the JPEG quality setting, completely disregarding its static nature, we could actually hone in on a compression quality that is far more efficient for a certain input image. And like I said, this is of course also brute forced, so it's not very nice, but this can also be done more efficiently. Cornell actually suggested to me, I think yesterday, that instead of using a binary search, I can use a different approach and arrive at the same result with 1 or 2 runs less. So this might even be done quicker. And there's really no reason not to do this, because I'm not forcing another encoder on you or something. I'm just using the encoders available to us right now. I'm just being smarter about what quality I'm feeding them. So this is really an easy piece of software, easy to use, and doesn't break anything. It's just being clever about what quality I'm shipping for which image. Oh, sorry, wrong screen. The tool is available on Bash as a Bash script right now on GitHub. I uploaded that yesterday. Finished this yesterday, uploaded it yesterday, I think. Yeah. So that works. You can just take this. The code is, I think, less than 300 lines, so very, very easy to read. It's not as bad as Adapt. Adapt is really, if I open Adapt right now, I'm like, I can't maintain this anymore. This has gotten too big. But this tool is really very tiny and easy to use. And it basically does the same thing as ImageMin did a couple of years ago. It just works right now. ImageMin doesn't. Another thing about adaptive JPEG compression is, imagine JPEG compression based on round trip times. Again, who says that JPEG quality needs to be static, right? So we can be smart about what JPEG quality we use depending on what's inside an image, so we don't incur artifacts. Or what we can also do is base the JPEG quality on the performance that an end user currently has. So if I'm out and about with my mobile, I probably have higher latencies than I have on my desktop or my laptop, unless, of course, I'm at conference Wi-Fi or hotel Wi-Fi, right? So there is actually a possibility on the Akamai platform to detect round-trip times and compress JPEGs dependent on that round-trip time. That's, I think, is a really, really neat trick. And this is basically how it looks like. This is, I think, Hawaii. Correct me if I'm wrong. And let's see if you can detect this. Yeah, there it goes. So this is a 10-step compression where you can see how the quality degrades dependent on the round-trip time. So there are 10 different degrees of quality being shipped dependent on how fast the connection is between an Akamai Edge server and a mobile user. The limits of that can actually be defined. So if you say you only care about people suffering from poor 2G, you can actually target that specifically. So this isn't even hard-coded. Does everybody know what a round-trip time is, by the way? Or yeah? Is everybody happy with the explanation so far? Great, thanks. Okay, so as you can see, this is another nice approach to ship highly compressed images to users who suffer from poor performance already. Right? If I'm on the train with my mobile and I want to read an article, I don't really care as much about the quality of the image right now. So I might as well get an image that is far strongly compressed than if I was on a high-speed connection with low latency, because I will just be happy that the page finally loaded. So let's compress that image strongly, ship it to the people already suffering from poor performance on their current device right now, and let's ship high-resolution images with good quality settings to people with low latency. This is something that's available on the Akamai platform. Right. Okay, if there are no more questions, I'll get into the Chinese takeaways. No? Right. So let's sum that whole thing up. Here's the complete result table, which we've seen last, 1 hour and 15 minutes. So let's recap. We've got JPEG Optim and Rescan with 12% compression efficiency, mean compression efficiency, and a very, very acceptable dissimilarity index, so low chance of incurring artifacts. We've got Google's WebP at a sweet third of mean compression efficiency, but of course it comes at a little price of higher dissimilarity. And as we discussed already, WebP can only be shipped to supporting browsers. So you have to detect this. Then the strong contender, which I support as much as I can in these talks, mods JPEG, hones in on 12.1% and a completely acceptable similarity though. Very nice. The proprietary solution, JPEG Mini, 17.2% and 0.4 dissimilarity, and Adapt, almost as good as WebP, but with high dissimilarity. So once mods JPEG, again, to sum this up, once mods JPEG gets adaptive compression, and we solve this adaptive compression with a saliency map, mods JPEG will for sure beat Adapt in both compression efficiency and runtime. And this is the point at which JPEG is the #1 thing to go for image compression. And for takeaways, for action items right now, if you leave this room, install mods JPEG. Easy to do, deployable, stable, works very well, and it's well maintained, gets updates, and as I said, it will be the #1 place to go to for JPEG compression in the future. Then keep up with saliency mapping. The whole issue of human-computer vision is becoming more and more important. If you see the numbers of papers published in university about saliency mapping, image compression, image optimization, based on saliency mapping, human-computer vision, both in static images and videos. The amount of papers is just going through the roof right now. This has gotten a lot of funding. It's very important because lots of entities in the world want this. Keeping up with saliency mappers to make image compression smarter is important. The maximum symmetric surround saliency algorithm is neat, but it's from 2012, created by one person. I'm pretty sure that if a smarter engineering team sat down, they could come up with something even better. So keep up with saliency mapping, because this is something that is really important for image optimization in the future. We need to be smarter about what we do with each input image. Then leverage something like CJPEG dissimilarity, because hard baking that quality metric, like we discussed, non-standardized, is a terrible idea, right? Don't do this. Be smarter about which quality you deploy. Either check out image min and finally fix it and get it to recompile again and push the source live, please. Or just use CJPEG dissim to make sure that you ship a quality acceptable for each input image instead of hard baking this. It's an easy step. Be smarter about what quality you ship for JPEGs. And about the more difficult stuff like shipping WebP, Microsoft's competition JPEG XR, or doing something like round-trip time calculations, use something like Akamai, the Akamai Intelligent Platform to handle this for you, unless you want to get into the deeps of device detection, making sure that you're shipping only to supporting devices. Thank you so much. That's it. Okay, questions? Draw.
Regarding percentages, so you said that the tolerable amount of tolerable dissim score is basically 1.5%. That's you said 0.05, so it's
Yeah, that's right, 1.5%. Yeah.
So basically all the encoders were below this, even adapt WebP, even though the ones that were with the relatively high distortion were below the threshold of visible distortion.
It's a really good point. However, from a human eye perception, I can tell you right now that the artifacts occurred by, oh, sorry, did everybody oh, okay, sorry, for the people in the back. The Neurostrata Radware research indicated that a dissimilarity of 0.015 is acceptable, which means 1.5%. Drav rightly mentioned that all the encoders we've seen on the result table are below that threshold, which is nice. However, I repeatedly said in the talk that several of the tools actually incur visible artifacts, like adapt, for example. So my answer is yes, they are below the threshold, but this is basically why I want a second study run on this, because I'm pretty sure that depending on the content of each input image, we will have visible artifacts. So I've played around with adapt a lot. And I can tell you that I've seen visible artifacts without really trying too hard, which is bad. I shouldn't be able to do this. So even although in a median result, adapt manages to hit below that threshold, there are still visible artifacts, which is not what we want. So that sweet spot of 1.5% dissimilarity has to be reevaluated, I guess. Yeah. Thanks. That's a really good point. My next step basically is running that adaptive compression with CJPEG dissim on the large data set. I had hoped to be able to do this for you guys right now. It didn't manage to process all the encoders. As you can see, it supports JPEG and JPEG Optim right now. Once I finished updating the script so it supports all the encoders, which were run through that study, I will run the JPEG dissim tool with all the encoders on the large data set. So I can also give you guys an idea of how much JPEG quality actually varies if you adapt it to input images. that would be my next step of research because I think that's really interesting to see. Right, if there are no more questions, oh, sorry.
So this might seem like a really naive question, because this isn't my area of expertise, but do you tend to want to run this kind of compression as the image is coming into your systems, or as it's coming out? So at the point of serving or at the point of upload, which if you've got a website, you're taking on images, at which point are you looking at?
So if you were to compress images on the origin, so your own server, you would do this while the images are being uploaded or after they're being uploaded. You would queue them and process them then. Actually, I don't know if anybody from Etsy is here right now, but Etsy is actually pretty good about these kind of things. They have open sourced a lot of their tools, and they also blogged a lot about how they're handling queuing, because they have these huge amounts of user-uploaded images, and they had problems being able to cope with their compression. So I think there will be probably a very good address to talk to about this. But yeah, the simple answer is you would compress on origin on your own server. However, of course, there are services for you who can take this off your shoulders if you don't want to implement or can't implement on the origin. I mean, there's plenty of scenarios where you don't have control of the origin. So there might be a need to use a third-party service such as Akamai to deploy images for you and compress them. Thanks. Okay, so if there are no more questions, I'm here all day. Just chat me up. I'm happy to answer all the questions about this, especially also if you think about how to implement this for CMSs. I might get into that with you in a one-on-one. I've actually built a WordPress plugin in the past to do this for WordPress. So if you have any questions about integrating this into your workflow or automating these processes, just chat me up later today. Thank you so much.